Okay, I think we are ready to start now. Welcome one more Thursday to our P&S on heterogeneous systems. Today we are going to cover one more parallel pattern. We are going to see how we can calculate or we can compute histograms using our GPUs. So before we go into the discussion about the histograms, let me very quickly remind you what we covered in our previous lecture. It was the parallel reduction. We were talking about the reduction operation, and remember that reduction is an operation that reduces a set of values into a single value. There are some good examples on the slide, like sum, product, minimum, maximum, and there are some properties that reduction needs to fulfill in order to be a proper reduction and to be implementable in a parallel way, as we explained the other day. The first of the properties is associativity, the second one is commutativity, and the third one is an identity value. In the case of the addition or sum, which is the operation that we use as an example in our previous lecture, this identity value is 0. And as you know, reduction is a key primitive for parallel computing. We were talking about how to implement a sequential reduction, assuming that we have an input array n, an input array A of n elements. In a sequential reduction, what we only need is a for loop to go through all the elements of the array and accumulate them on some variable. But the good thing here is that there are many operations that can be independent, and this is why we can think of a parallel reduction. And one efficient way of implementing a parallel reduction is by using a tree reduction. In the tree reduction, and especially if we directly talk about how to implement it on GPU, what we can see is that we are going to partition the input array A into different chunks, and each of the chunks are going to be assigned to the thread blocks, thread block 0, thread block 1, and then internally we will assign the elements to the threads that belong to the warps that compose the thread block. And then we can start the execution. First of all, we will have some threads reducing pairs of values, adding pairs of values, and storing them in some storing these partial results in some temporary storage. For example, the shared memory or the registers that we find in the GPU cores or streaming multiprocessors. We will need intra-block synchronization in order to make sure that all threads in one block have finished the computation in each iteration, because these partial results are going to be reused by the remaining threads that continue the execution in the next iteration. And here we have another intra-block synchronization point. And finally, an inter-block synchronization is needed because it's the way that we have to synchronize two different blocks so that we can end up reducing the partial products that have been generated by the partial sums that have been generated by the thread blocks, in this case, block 0 and block 1. Remember that one way of doing this inter-block synchronization is by terminating the kernel, and then we can do the final reduction either on the host CPU, or we can launch a new reduction kernel on the GPU. And we also talk about another possibility, which was using atomic operations in global memory. Essentially, this means that we have one memory location in global memory that is going to be updated by one thread from block 0 and one thread from block 1. And using atomic operations ensures that there are no data races and the final result is correct. As usual, please don't hesitate to stop me and ask questions whenever you need it. We also talk about how to implement, so how to map the procedure that we just discussed in the previous slide, how to map it inside each thread block. And we first talk about a naive way of doing it, which is using even number threads to perform the parallel reduction, to perform the reductions in parallel. And iteration over iteration, we see that half of the threads retire, right, as you can see on the screen. But we saw that one problem with this program is its low SIMD utilization. And the reason is that iteration after iteration, threads from all warps start retiring. And this means that the utilization of each of these individual warps reduces as we make progress and go to the next iteration, as you can see. So we were discussing how we can avoid the warp underutilization or the low SIMD utilization that we have in this program. So we talk about a different way of doing the mapping. In this case, what we are doing is using consecutively numbered threads that belong to the same warp, or are going to belong to the same warp. And this way we are going to be able to reduce the intra-warp divergence very significantly. You may remember this code with a high SIMD utilization, and in this code, iteration after iteration, we see that half of the threads retire, but the threads that retire belong to different warps from those that continue the execution. Good thing of that is that here in this stride 8 iteration or second iteration, these two warps are completely utilized, so 100% utilization here, same as here, 100% utilization in this last iteration of warp 0. So this is the way that we can maximize the warp utilization. And we also talk about another, like the next optimization step is using warp shuffle functions. Why is that? Because in the end, at this point, we are only using a single warp, right? So and because threads belonging to the same warp execute in lockstep, it's not really necessary to use intra-block synchronization as we had to use in the initial iterations. And especially there is a way of communicating across these threads that belong to the same warp. And this is what we call the warp shuffle functions. So warp shuffle functions are a way of sharing data among threads belonging to the same warp without using shared memory and without using sync threads. And these warp shuffle are expected to be significantly faster than the access to shared memory and the use of sync threads. There are different variants, as we discussed the other day, and this is the reduction with warp shuffle that we explained. In the very beginning, what we do is loading the data into the shared memory. Remember that we can even have each of the threads reading 2 elements from global memory, 2 elements at a certain distance from global memory, and adding them together and store the result. We already have our first partial result in shared memory. Then we need to synchronize, and then it comes this reduction tree in shared memory that is optimized because it doesn't have intra-warp divergence. And then we synchronize after each iteration. And when we are done with this, and there is only a single remaining warp to finalize the computation, to finalize the reduction, we can start using the shuffle instructions as you can see. And finally, one single thread stores the result somewhere in this partial sums array that resides in global memory. And we also talk about other ways of doing the optimization or other, let's say, techniques that we can apply to the reduction. For example, we talk about the atomic operations. I actually mentioned them in one of the previous slides. We can use atomic operations in global memory or in shared memory, and this can be one more way of optimizing as we discussed. And today we are going to talk much more in detail about atomic operations, and we are going to talk about another important operation or another important parallel pattern that can be, and it's typically implemented using atomic operations. But first of all, let's remind what an atomic operation are. CUDA supports atomic operations on shared memory and in global memory. They perform read, modify, write operations atomically, and this means that when the atomic operation starts, read, modify, and write happen consecutively without any other instruction being executed in between. And remember that there are arithmetic functions implemented by the atomic operations like adds, addition, subtraction, maximum, minimum, exchange, increment, decrement, and compare and swap. And this is the typical syntax in this case of an atomic add. This is a pointer to shared or global memory, depending on where the specific array resides and the specific pointer is pointing to. This atomic operation will be executed near in the global memory or in the shared memory. So this is the pointer, this is the value that we are going to add in this case, and this is the return value. The atomic operation returns the old value, so the value that was stored in the memory address pointed by this pointer before performing the addition in this case. Remember that there are also atomic operations for bitwise functions and or an XOR and different data types. Actually, the data types depend on the atomic operation as well. So if you are you really want to use them, I would recommend you to check what are the data types supported by different atomic operations, and you can find this in this link from the CUDA programming guide. Okay, but what's the problem with the atomic operations? The problem with the atomic operations is that the execution gets serialized if there are atomic conflicts. So we may be in a ideal situation like this one. We have two different threads. One of them has to update element 0. The other one has to update element 2. And because they don't collide, there is no conflict or collision here, they can perform the atomic operation at the same time, loading, updating, and storing. And this will take some certain latency. Let's call it T-base. But there will be other cases, and there will be quite frequent sometimes, where threads need to update exactly the same values in memory. So in this case, for example, thread 0 and thread 1 have to update element 2. So this implies that the execution of both threads is going to be serialized. First, thread 0 will update the corresponding memory location, then thread 1 will do it, and this entails that the total latency is not only the T-base, the base latency, but also some additional latency due to this conflict. How large is this T-base and also this T-conflict? Of course, depends on the architecture. And one thing that we have observed, we have noticed over time, is that the cost of each conflict is less, is lower, as the cost of each conflict is lower as the architecture improves and generation over generation. But yeah, essentially that's the thing. If there is no atomic conflict, we can have concurrent updates. If there is atomic conflicts, we will have serialized updates. And how are we going to use atomic operations? Well, I'm going to discuss very briefly different programs where we can use atomic operations. This is not a rigorous classification, and I'm not intending to do so. I just want to give you some examples of when atomic operations can be used. For example, we can use atomic operations for computation. And what I mean here is that the atomics are executed on an array or certain memory locations that will contain the output of the kernel. For example, in the parallel reduction, if we are using an atomic operation to reduce the final partial results from different thread blocks, what we are calculating with the atomic operation is the final result of the kernel, right? And a similar example is what we are going to see today in histogram calculation. But atomics are also very useful to carry out synchronization, to synchronize different threads or different thread blocks executing at the same time on the GPU. So we can use these atomic operations also for synchronization or coordination in the form of flags, logs, counters, etc., etc. Today, we are going to very briefly talk about one example, which is a string compaction, where we can use a counter, and this counter is essentially tells every thread where they have to store the output value, and different threads, before storing a value, update the counter, and then they write in the corresponding the right location, right? So this would be a use of the atomic operations as a synchronization primitive. In the end, the most important thing to keep here into account, keep here in mind, is that we should use atomic operations wherever we want or need to prevent data races, which happen when more than, or may happen when more than one thread needs to update the same memory location. But very, very quickly, let's review what we call a data race. A data race occurs when multiple threads access the same memory location concurrently without ordering, and at least one access is a write. One access is a write because doing a write means that we are modifying one value and the other threads might be reading a wrong value at some point. Data races may result in an unpredictable program output, and I'm going to show you here one simple example. Imagine that we have two threads, thread A and thread B, and what they are doing is calculating a histogram, for example. They have to update certain position of the histogram called one bin. And actually what you can see here is that we are reading one bin and we are adding one, and then we are storing the result. That's what thread A is doing, and also thread B is doing the same. The problem is that depending on how these two threads execute the instructions, we may end up having as a result value 1 or value 2. And let me show you actually two examples here in this slide. Thread A, so in the first case, thread A executes all 3 instructions, and then thread B starts the execution of all 3 instructions. And the second example is the other way around. It's first is thread B that reads, modifies, and writes the value in bins B, and then it's thread A. In this case, the final result is correct because the final result is 2, and both threads are, one of them operating first, the other one operating later, and there are no interleaved instructions from these two threads. So that's why the result is correct. But we may also have something like this, especially in multi-threaded architectures where threads can be scheduled whenever the scheduler decides. For example, when some data is ready, and there might be multiple threads at the same time that are ready for execution. It might happen that the threads, the execution of instructions from the different threads or by the different threads is interleaved in a way as you can see here. So first of all, thread A starts and reads from memory this bins B, then it updates the old value, adding 1 and storing into this new val. And then at that point, thread B also reads bins B before thread A has written the new result. And this happens that thread B is already reading a stale value or a wrong value from the old value from bins B. So when thread A writes into bin B, thread B doesn't have the chance to use the good value, the updated value that thread A already wrote. And it could be in a different way. So it could be different as well. In this case, it might be thread B that starts the execution, reads something from memory, updates, and at that point, it's thread A that reads this same value from A, and it's reading an old or stale value. And in this case, in both cases, actually in both scenarios, the final values of bins B will be 1, and this is wrong. And this is why we need to find a way of making sure that either that these 3 operations here are executed atomically. They are executed at once without other instructions from other threads interfering. What we typically use in parallel architectures is what we call mutexes or mutual exclusion. In this case, if we have 2 threads that need to update a certain value bins B, what we do is using this mutex lock, that this is a library call or an API that goes to a certain log, a certain value in memory, updates it, sets it to 1 so that the access to this critical section is locked, and then we can proceed with the execution of the critical section, and at some point the mutex gets unlocked. So mutexes are very much used in parallel architectures, but in principle they are not a good fit for SIMD execution because they may cause deadlock because of the fact that threads in SIMD execution are executing in lockstep. So it could happen that one thread updates the log while other thread is already so one thread updates the log, and this impedes that other threads make progress because they couldn't go through the critical section. But mutexes, as I said, are useful in many multi-threaded architectures. One example of fine-grained multi-threading architecture that uses mutexes is the UpMem-PIM architecture, the processing in memory cores that UPMEM architecture has are fine-grained multi-threaded. They can execute multiple threads cycle after cycle. Essentially, they can have up to 24 threads because they have 24 thread contexts. So here, what it happens is that every single cycle, this dispatch unit is fetching one new instruction for a different thread from this instruction memory and starts the execution and executes this instruction onto the pipeline. Whenever they need to synchronize these threads that are called passlets in its architecture, need to synchronize, they can use or need to access a critical section, a concurrent data structure, for example, they can use mutexes for these concurrent read, modify, write operations. And if you want to learn about this UPMEM architecture, I can recommend you this recent paper that we wrote, and there you can actually find implementations of histogram, which is the parallel pattern that we are studying today. We will talk later, but first of all, how are arithmetic operations implemented? There may be different ways, and as I said, this is something that we are going to see later. We are going to talk in detail about how atomic operations are implemented in the last part of this lecture. But one thing that we know is that the ISA has evolved with the GPU architecture generations. Remember that this is the syntax in the high-level programming language in CUDA. This is the syntax in the intermediate representation that is called PTX in NVIDIA GPUs. You can clearly see here that this is an atomic operation on shared memory. It's an addition, and in particular, this one is operating on unsigned integers, unsigned 32-bit integers. This is the register that will contain the return value, the old value. This is the pointer to memory, and this is the value to add. But if we go one level deeper, we will reach to the assembly code. We will reach to the machine level code, and we can see that the way that these atomic operations are implemented has changed over time. In the earlier architectures, by the way, this is all for shared memory, which is corresponds to this PTX instruction that we have here. We will also talk about the global memory atomic operations later as well. So yeah, so this short sequence of code, these 4 instructions that we can identify here correspond to the older architectures, and essentially here, what the hardware was using was a series of tiny locks, like small lock bits that were updated by the threads at the same time that the memory read or the memory load happens. And in that case, and it's generated one predicate, and this predicate determines what are the threads that are going to continue the execution. Here you can see this load and lock operation, addition operation to update the value in memory, and this store and lock operation. And after that, one branch instruction for the threads that didn't succeed in the first try to acquire the locks, they can jump and continue the execution. But as I said, we are going to talk more in detail about this later. After the Maxwell, with the Maxwell architecture, the hardware starts supporting native atomic operations in shared memory, which have this syntax is just a single instruction. As you can see, is an atomic operation in shared memory. This is an addition, and in this case is a return value and a pointer to shared memory and the value to add. So this change, and we will see that this also this hardware improvement also causes good performance effect, as you will see. But anyway, recall that about the uses of atomic operations. We're going to use atomic operations wherever we may have concurrent accesses, concurrent updates to a shared memory location. And we already discussed one example of this in the previous lecture, which was the parallel reduction. Remember that I mentioned 4 different versions of the parallel reduction that you can find in the CUDA samples. And also remember that I explained you that we could implement some of these versions using atomic operations, right? And some of them can produce pretty nice results. And we even studied this in one of our recent papers, different implementations of reduction using global, shared memory atomics, shuffle instructions, and so on. And this is the paper in case you want to take a look. So we already know, we already have our first example of where we can use atomic operations, but now we are going to talk about another important example, and probably more important for the use of atomic operations, because rarely histograms are implemented without using atomic operations. So a histogram, you may be familiar with a histogram is that a histogram is a frequently used computation for reducing the dimensionality and extracting notable features and patterns from large data sets. In the end, one histogram is a way of representing the data that some input data set contains. So for example, in images, a histogram is a count of is an array that has different bins, and each of the bins corresponds to the count of the values in the pixels of the image. And this can be useful for many, it's useful for many image processing applications, for example, for feature extraction for object recognition, but it's also useful in different fields, for example, in banking or also in astrophysics. So a basic histogram is that for each element in the data set, we use the value to identify a bin to increment. So what we do is, first of all, dividing the possible input value range into bins. So for example, let's go back to images. You know that images are composed by pixels. Each of these pixels, the pixels have a certain depth. In a simple case, we can assume that these pixels are 8-bit. So if they are 8-bit, they can have 256 different values. So if we want to create the histogram of an image with 8-bit depth, we will need 256 pixels, and it's 256 bins. And we associate a counter to each of the bins, or we can say that the bin is a counter. And for each input element, we examine its value and we go to the corresponding bit and we add one. We increment the counter of that bin. And this way, when we go through the whole image, we will have the complete histogram, the final histogram, which will give us a distribution of the pixel values of that particular image. If we want to compute the histogram sequentially, for example, this sentence, I calculate a histogram. I want to count the different characters that compose this sentence, and this is going to be my histogram, right? So you notice that we have a different bin for letter A, or for the space A, B, C, D, etc. And because it's a sequential execution, we are only going to use a single thread of execution. There is just one thread in our program. So in the first iteration, we read the first element of the sentence of the input array. We analyze, we check the value, it's letter I. So we go to the bin I and we increment. And then iteration 2, iteration 3, and iteration 4. And as you can see, the execution is sequential, but after having gone through the whole sentence, we will have the complete histogram at the bottom. And if you want to see how the code for this sequential histogram looks, it's a function like this. Here we have some, the input arguments are the histogram, the input image, or the input for which we want to generate the histogram, and the size of the input, or the size of the image if we are talking about image histograms. The only thing that we need is a for loop to go through all elements of the input, read the value, and then depending on what's the value, we will update the corresponding bin of the histogram. As you can see, after that, we increment the index, we go to the next element, and so on. But now what if we want to implement a parallel histogram? We want to do it in parallel. We want to do it on a GPU. In this case, we are going to have more than one thread. Let's assume that we have 4 threads to calculate the histogram for this sentence. So first thing to do is that these threads will typically read adjacent characters or consecutive memory locations of the input array. Good thing of doing this is that if these threads belong to the same warp, we are reading all these elements in a coalesced manner, which means that we are maximizing the bandwidth that we can achieve from DRAM where the image or where the sentence in this case is stored. And then each of them goes to, examines the actual letter that they read, and they go to the corresponding bit and they increment the corresponding bit. And this is this would be the first iteration of the calculation or computation of this histogram. And this could be a parallel kernel implementing this operation. Observe that again, here we have the input array, the pointer to the histogram, the input size. And now, instead of having instead of having a single index in the sequential execution, here we have an index per thread, and we calculate the index for each thread depending on, as you may remember, the block index, the dimension of the block, and the index of the thread inside the thread block it belongs to. And we also have a stride, which is the total number of threads, because every thread, after reading one element, will have to go to the next element to read, which is far away as far as the total number of threads that are taking part of the computation. Similarly, as in the sequential code, we have this while loop, and inside the while loop, again, we read and we update the corresponding bin of the histogram, and then we update the index and restart the execution until we are done with the whole input or with the whole image. But there is a problem in this code. That's why I'm saying here that is wrong, right? And it's because the reason is that we are not using the right instruction here in this line. In this example, you can see that after the threads move to the next element, there are some conflicts that appear. And this conflict is essentially a data race. If we are not using atomic operations here, we may have a situation similar to the one that we was described before when we talk about the data races, because this thread 0 and this thread 3 have to read, modify, and write the same histogram bin. So we definitely need to use atomic operations here to ensure that there are no data races and the final result is correct. So essentially what we have to do in the code that we have just seen is, instead of using a simple addition, we have to use an atomic addition. Guys, are there any questions? Okay, I also don't see any questions in YouTube. Everyone is welcome to ask. I will be checking from time to time. Okay, so as I said, we have to replace the conventional addition with an atomic addition, but now we have another problem. And the problem that we have is that these atomic additions are not very efficient, as you know. Whenever we have a conflict, we are going to have a serialization, but also there is one more thing, is that this histo, because it's one of the input arguments, this histo resides in global memory. That's something I know. And atomic operations too in global memory are going to be pretty costly, right? Because remember, an atomic operation is a read, modify, and write. And if you remember from the day where we discussed, when we presented the memory hierarchy, the off-chip memory, the DRAM, the global memory, is far away from the processors, right? So this means that if the latency of access to memory is 500 cycles, we need 500 cycles to bring this particular value, histoval, from global memory to the compute unit, and then we add there, and then we have to write back the final result, or this updated bin onto the histogram, right? And that is extremely costly, and as you can also see in this slide here. So this load modify store has 2 full memory access delays. So we have to pay the DRAM delay first, then this transfer delay over the off-chip bus, and then we have some internal routing, and then we finally can update the value, and then we have to write back, as you can see. So this takes so long, and especially if then there is another thread that needs to update the same value, it will be even worse, right? Because we are going to repeat the whole process of DRAM delay and transfer and internal routing again and again. Some hardware improvements appeared back in 2010 when the Fermi architecture incorporated an L2 cache. In that case, there was a, say, free improvement for the global memory atomics, because in this case, let's say that the access could happen from L2 instead of having to go to DRAM, to the global memory. And this obviously resulted in some reduction of the latency and some significant performance improvements on the programs using atomic operations. But still, there is a realization, and still the L2 is not that close, right? So you still have to go to L2, and this definitely also takes a few cycles. And if you want to optimize even more, you can execute the atomic operations even closer. In this case, not in global memory, but in shared memory. But still, there is a problem that the shared memory, I mean, the accesses, if there are conflicts, will be serialized. But anyway, as I said before, we will talk more in detail about the evolution of atomic operations, the hardware and the architecture, and how the different improvements have been applied to make the atomic operations much more efficient and much more performant as they were in the earlier generations of the CUDA-capable GPUs. Now, let's continue talking about the histogram. And as I said, we are going to use today image histogram as a running example, let's say, because histograms are very much using image processing. It might be possible that it's not only reading one pixel and then examining the pixel and then voting in the corresponding bin. It might be possible there is also some optional computation. As you can see, we would be calculating a new value related to the pixel and then updating the corresponding bin of the histogram. But as you know, we in the generation of this histogram need to use atomic operations because it's very likely that we will have atomic conflicts among the parallel threads creating or generating the image histogram. And actually, these atomic conflicts are going to be quite frequent in the histogram computation of natural images. Why is that? Because as you can see, there is a special similarity of the value of the pixel distribution in the natural images. And if you observe even closer here, this image, you will see that there are many pixel values that are repeated. Like, for example, these two here that are going to be accessed by neighboring threads. And if these threads are neighboring, they are likely belonging to the same warp. And if they belong to the same warp, this means that they are going to, or trying to update the histogram at the same time, and this will cause an atomic conflict. So one way of optimizing the execution or the calculation or computation of histograms on GPUs is by using a technique that we call privatization. Privatization means that we are going to use multiple subhistograms at the same time, and different threads are going to update the different subhistograms. As when the subhistograms are complete, we will have some procedure to reduce, to merge these different subhistograms and obtain the final histogram. So this is privatization, an optimization technique where multiple private copies of an output are maintained, and then the global copy is updated on completion. We require here that the operations are also associative and commutative, but that's not a problem in the histogram calculation, because what we are using is the addition, and there are advantages. The first advantage is that we reduce the contention on the local copy. It's not the same having a single histogram in global memory and having all threads executing on the GPU, accessing and updating the bins of this single global histogram. We can reduce the contention if instead of using a single histogram, we use more, right? Because we have more space to distribute the potential conflicts. So we will end up having less conflicts. And also the good thing is that if the histogram is small enough, the private copy of the histogram can be placed in shared memory, which is way faster than DRAM, as you may remember, or as you may know. So privatization for the histogram essentially consists of creating multiple subhistograms. The first approach that we are going to take here is dividing an image into chunks, assigning each of these chunks to different thread blocks, as you can see on the slide, and each of the thread blocks can later update their own subhistogram that resides in shared memory. So in this case, it's a very simple, I mean, in this case, it's just a histogram of 4 elements, only 4 beans, but this is the subhistogram corresponding to block 0, subhistogram of block 1, block 2, and block 3. And when the blocks are done with the computation of their subhistograms, they will synchronize in some way, and we will need to do a parallel reduction to compute the final histogram that in this case will reside in global memory. And another technique that we typically apply to histogram calculation as well, together with privatization, is coarsening. In coarsening, what we are essentially doing is instead of assigning each of the chunks of the image to a different block, we assign multiple chunks to the same block. So this block 0 starts with this chunk, and when it's done with this chunk, it goes to the next chunk that has been assigned to it, and then goes to the next one, and then goes to the next one. This is going to give us quite a good performance if, of course, we are occupying all the resources on the GPU. Of course, it doesn't make sense to use coarsening if instead of using all the GPU cores, you're only using half of the GPU cores because you decide to launch fewer thread blocks than the maximum number of thread blocks that you can have concurrently executing on the multiple cores. That's for sure. You're only going to use coarsening if you can really use all the available resources on the GPU, use all the GPU cores at the same time. But then, instead of having to wait for a thread block to finish, to schedule another thread block, what you can do is tell this thread block that is already scheduled, go to the next chunk of the image, read it, and continue computing the histogram. And in the particular case of the histogram calculation, this has some advantages. The first advantage is that we don't need to allocate so many subhistograms. We just allocate in shared memory 1 subhistogram per block, and then we initialize this subhistogram only once. That takes time, right? This initialization takes time. So we only initialize the histogram only once. And when the thread block, in this case, block 0, is done with this chunk here, this here, this here, and this here, and we really have the final subhistogram, then we can perform the parallel reduction. In this specific example, we only need to reduce or merge 4 subhistograms, right? But if you count the number of chunks that are in this image, and we assign each of the chunks to a completely different thread block, the number of subhistograms that we will have to merge will be much larger, right? And in that case, this parallel reduction is going to be costlier. So this is one of the advantages of using coarsening, at least in the context of histogram computation. And here you can see our, say, final code for the parallel histogram kernel with privatization and coarsening. Again, here we have our thread index that is calculated with the block index, dimension of the block, a number of threads, and the thread index inside the block, the total number of threads executing this histogram kernel, and here we declare the subhistogram, this histo_s of size beans, which is the size of the histogram, the total number of beans. First thing that we have to do is initializing the subhistograms, all the subhistograms, and all the threads that belong to this thread block that are going to update later this histogram can collaborate in this initialization. We have to make sure that all counters of the histogram or beans of the histogram are equal to 0 before going to the actual execution. That's why we need this intra-block synchronization here. And then we go to the main loop where all threads are reading one element from memory that belongs to the image, inspecting its value, and depending on its value, updating the corresponding bean in the subhistogram that resides in shared memory, this histo-S. When all threads are done with all computation that is assigned to this thread block, again, we have to sync thread. And finally, we will have, in this case, the parallel reduction is done in a simple manner, just using atomic additions in global memory, as you can see. So we will have all threads of this thread block reading one bin of the subhistogram in shared memory and updating the corresponding bin, the same bin, in the final subhistogram, in the final histogram in global memory, as you can see. There is, this is, let's say, like how to say? It's like the classic implementation of the parallel histogram kernel with privatization in shared memory, as you can see, and also in this case, using coarsening, because if we are not using as many thread blocks as chunks, as I discussed in the previous slide, we would be reusing these subhistograms in shared memory again and again and again. And when the whole image has been gone through, when this I reaches the input size, we can perform the parallel reduction here. Okay, yeah, but one last thing, there is always a little bit more of optimization that we can apply. And in this case, I'm going to show you one relatively novel way of optimizing the atomic operations and optimizing the histogram, which is by using warp synchronous programming. We are already familiar with warp synchronous programming because we already know the warp shuffle functions that we have used for the parallel reduction. We are going to use this warp shuffle in the a small procedure that I'm going to show you, but we will also use some other warp synchronous primitives that are available in CUDA. For example, this one is pretty interesting. Remember that GPUs are SIMD engines, and SIMD engines, the way that they handle divergence is by using a mask, and this mask tells us in any particular time what are the threads that are active, what are the threads that are really executing the control flow path, right? And there will be other threads that are idle and will probably execute other instructions, other control flow path later. So if we want to know what's the mask, what are the threads that are active, we can use this instruction or this primitive active mask that returns the mask of the converged threads. Or for example, we can use this match all sync that returns true if all participating threads has the same value. All participating threads will be indicated by using this unsigned value, which in reality is going to represent the mask of the threads that we want to get involved in this operation. And what we do here is checking what are the values that are using. So what are the threads that are using the same value here? And this, by using these warp synchronous primitives, we can come up with this simple function, this atomic add. As you can see, it uses atomic operation, of course, but what we are going to do first before executing the atomic operation itself is checking what are the values that we have, that each of the threads need to update, need to add, and where they have to add them, what's the pointer that is going to be used by the atomic operation. And if there are threads that share the same pointer and they're going to update and are here to update the same memory location, we can perform a reduction first and then use the atomic addition. And this way, we are going to reduce the number of atomic additions, and in the end, we are going to reduce the serialization. Let me explain you this code very briefly. This atomic add is going to be, it's like a short function, as you can see, is what we typically call a device function that is going to be called by each of the individual threads, executing a longer program that needs to use atomic operations at some point. And as you can see, the input parameters are this pointer, which is the pointer to the memory location that needs to be updated and the value that it's going to be added in this case in this memory location. So first thing to do is to check what are the active threads. Remember, we may have thread divergence, so we may have some threads going through some control flow path, other threads going through a different control flow path. So when executing this instruction, first thing to know is what are the threads that are active, and then we check the pointers of these active threads, as you can see. So what we are doing with this match any sync is for all the active threads, checking whether they have the same pointer or not. And if they have the same pointer, a flag will be set in this new active mask. By doing this, or by using this, now we can call this reduce warp function. Remember that we talked about this at the very end of the previous lecture. These are new reduction functions that are included in recent versions of the CUDA SDK and supported by the newest generation. So they can execute the reduction pretty fast. So for the threads that are active now, which are the threads that are sharing the same pointer, we are going to reduce all the values that they have to add and obtain some partial value that is the value that we are going to end up adding here using the atomic operation. This atomic operation is only executed by a single thread, and the thread that executes this atomic operation is the thread that is the first active one in the mask. You can check the meaning of this. FFS is the first set bit or first set flag in the active mask. So if you have an active mask where the, let's say, threads numbered with the most, the highest numbered threads like 31, 30, 29, etc. Are zero. These flags are zero because these threads are not active. This instruction here is going to find the first bit that is set in the active mask. Then it compares it to the lane, the actual lane of the actual thread that is executing this code, and that one, if you are that one, you will execute the atomic addition, and this returns a value, and this value can be later shared with the rest of the threads in the warp by using this shuffle sync instruction that we already know. This is just, as I said, one extra optimization that you can apply to your atomic operations, and it could be potentially applicable to the histogram computation as well. Okay, we are done for now with the explanation of the parallel pattern itself. I don't know, guys, if you have any questions. And if not, I'm going to continue. It will take a few more minutes to talk, to explain you the evolution of the architectural support for atomic operations. We are going to see how the hardware for atomic operations, both on shared memory and on global memory, has evolved over time, generation after generation, since the first CUDA capable generation back in 2006 or 2007 until today. Or until not today, because I think that the latest generation that doesn't really have any updated improvements for the atomic operations. But yeah, anyway, they keep incorporating the latest hardware that we are going to explain now. So remember, the architectural support for atomic operations has evolved across GPU generations. Remember, this is the syntax in CUDA. This is the PTX, or the intermediate representation, and then we have the assembly. How does it look? In shared memory, the atomic operations in shared memory for the first 3 generations of CUDA capable devices, Tesla, Fermi, and Kepler, consisted of a number of instructions. In this particular case, 4 instructions. As you can see, a load and lock instruction, an addition in this case, because this is an atomic addition, to update the value that has been fetch from memory, and then a store and unlock instruction to write back to memory. And then finally, for those threads that were not able to acquire the lock, we have a branch instruction and go to the beginning of this loop and again try to load the value, try to to get the lock, try to lock the access to that particular memory location, and so on. In Maxwell, we have the native atomic operations that appeared, and they continue existing in Pascal, Volta, and later architectures. These are a single instruction. They are not all supported natively. Only 32-bit integer and 32 and 64-bit atomic compare and swap. Other instructions still, all atomic operations still require several instructions for the execution, but I think that it's quite significant and interesting that we now have native support for atomic operations, as you can see in the latest generation. But let's first talk about how this was implemented in the older generations. And if we just take a look at this picture here, you can easily identify some processing engines. These processing engines are kind of GPU cores, and they have access to the shared memory, as you can see. So if we take a closer look at the shared memory in this picture, we identify the storage resource, which is the memory array itself, but also we identify this memory lock unit. And this memory lock unit contains some lock bits. So these lock bits are going to be accessed by this load and lock operation to try to for each individual thread to try to lock one shared memory location and have exclusive access to it. The good thing of this load and lock instruction is that the access to the storage resource happens at the same time as the memory lock unit is operating and assigning the lock bit to one of the concurrent threads, right? So we are not really wasting cycles for using the lock bits. It's just the cycles that we need to access the data from the shared memory itself. And after that, we generate what is called a predicate. Remember that we have also talked about the predicated execution. This predicate is kind of a, you can see it as kind of a software mask. So this predicate is going to contain 0 or 1, depending on whether the corresponding thread was able to acquire the lock or not. If it acquired the lock, then we have 1 here, and this 1 here and here will mean that this integer addition is executed, and this store and unlock operation is also executed. And after that, we generate a new predicate, and for those threads that are that don't have this new predicate set, they will jump to the beginning of the loop and try again to acquire the lock until they succeed and they can update the corresponding memory location. But let's take a closer look at these lock bits. So remember that the shared memory is a banked or interleaved memory where we have multiple banks. This is typically 32 banks. This is bank 0, where we can identify here address 0, address 32, or address 1024, and these are the rest of banks. And if we and one thing that we can do here is dividing, or considering that the memory is divided into pages of 1024 elements. So this one here would be page 0, this one is page 1, page 2, and so on. And we also know from the previous slide that in shared memory we have the storage resource, and also we have a memory log unit. And in the memory log unit there are some log bits. In total we have here in this picture we have 1024 log bits. So as you can see, if we take any address, for example, address 1024, this part here points to the page, this part here points to the row, and this tells us what's the bank. And now we can also check where is address 0. In address 0, it's in page 0, row 0, and bank 0. And this is address 32, is in page 0, row 1, and bank 0. So if we focus on these two, 1020, 1056 and 0, we see that they share the bank bits. They are in the same bank. And what this means is that when accessing these two addresses, we will incur a bank conflict. But that might be even worse if not only the bank bits are the same, but also the row bits. If that's the case, as for example, we can see in 1056 and 32. 32 is here, 1056 is here, and the problem is that these two guys are sharing the same log bit, as you can see. Or for example, here, this log bit 0 corresponds to element 0, element 1024, element 2048, and so on. And what does this mean? What this means is that if it turns out that we have two threads, one of them accessing element 0 and the other one accessing element 1024, because they both are sharing the same log bit, the effect will be the same as a position conflict, will be the same as having both threads updating the same memory location. So in the end, the problem with this log bit based mechanism is that the number of log bits that we have is limited. And because of that, we may incur atomic conflicts without existing a position conflict, without having threads trying to access exactly the same value. They may be trying to update different values, but because they're sharing the log bit, we have an atomic conflict. And this is the how the code looks. Let's check it closer. I already explained, but you can see it better here. This is the load and lock instruction. The load and lock instruction loads from shared memory and sets one log bit. There will be some threads that will succeed, and there will be others that don't. If, in the case that there are more than one thread trying to lock the same log bit. In that case, we have the predication register. We will have either 0 or 1 in the predication register. This predication register essentially is like 1 bit per thread. So here with this returns 0 or 1, and based on that we will execute the integral addition and the store operation or not. And the store operation, as you can see on the screen, stores the value that we contain here in register 10, stores it if the predication register is 1, obviously, and then unlocks the log bit and releases it so that other threads can attempt to acquire the log again after this branch instruction that takes them to the beginning of this loop. As I said before, the number of log bits is limited, and this is what causes the high contention that we found in the Tesla architectures and Fermi and Kepler as well. It was even worse in the Tesla architecture that only had 256 log bits, and here in this picture you have more or less the same effect that I explained before. There you can see here some threads that are to update element 0 or address 0, address 32, 1, or 1024, 2056, and so on. And as I explained before, if you check the bits, you will see that some of these addresses share the same row and page bits and row and bank bits. And this means that, so for example, this 32 here and this 1056 here, and this means that they go to the same log address, and because they go to the same log address, we will have contention here. This hash function that is described, of course, in this paper, but also in the patent where we based our study of these atomic operations in shared memory, this hash function in the actual implementation that we analyze is just a linear hash function, but it will be possible, as we are going to discuss later, to have more complex hash functions that can avoid some of the conflicts. And here in this slide, I'm not going to go through it in detail. I will leave this to you for your own study and understanding if you want, but more or less explains what's the whole process of the execution of these sequence of instruction that we have here. Observe that the first instruction is the load and lock instruction. We have multiple threads that are involved in the operation. They are accessing certain addresses, but they are also causing bank conflicts. Remember that here we have the access to memory at the same time as the access to the log bits. So if there are, for example, address 0, 32, 1024, and 1056, that belong to band 0, here we have band conflicts. And at the same time, we will have that only one of the threads that needs to access those memory addresses that share the same log bit can really really succeeds when acquiring the log bit and can continue the execution. And that's the reason why, for example, you don't see, sorry. That's the reason why, for example, you don't see that thread 4 is active here. Thread 4 is not active because the log was acquired by thread 0, right? So observe that thread 0 and thread 4 have to update the same address 0. So only one of them succeeds, and only one of them can execute the predicated addition, and then the corresponding store and unlock operation. And here we have the branch, and the execution continues because the remaining threads, those that didn't, that couldn't acquire the lock, have to try again, and so on and so forth. And if you check the paper, you will also get a better understanding of these tags or these labels that you can see here, and the meaning of these T-base, T-position, T-bank, that you can already imagine what they mean. Okay. And actually we did like a thorough analysis of these atomic operations in shared memory by using a micro benchmark. It's a very simple micro benchmark. As you can see, we need obviously to use an atomic add on some array HS in shared memory, and we repeat this operation many times in order to have a more precise count of what's the total number of cycles that we need to execute these operations, because we are counting the number of cycles with this clock instruction here to start the timing, and this clock instruction here to stop the timing, right? And after that, we will average after 256 atomic additions. And if we clearly tried many different patterns here for these boats, for these input data, we tried many different patterns, and one of the patterns that we tried was a pattern with position conflicts, which means that we have multiple threads in the same, more than one thread in the same warp that need to update the same shared memory location. And in particular here, we call N the number of threads that access the same address. So the number of threads that are really causing an atomic conflict. And this goes from 1 to 32. And one clear observation when measuring the latency in clock cycles is that the more threads try to update or have to update the same position, the larger the latency will be. And as you can see also, the step from in this stairway that we have here are more or less of the same size. The distance between each of these two dots is 120 cycles. And that's what we call the overhead of a position conflict in this case, because we have 2 threads or 3 threads or up to 32 threads trying to update the same shared memory location. So in that case, of course, using the same lock bit, so they have to repeat the whole loop of 4 instructions: load, update, store, and branch. We have to repeat it as many times as the number of conflicting threads. But because these threads belong to the same warp and they are accessing shared memory, they may also cause bank conflicts, right? And in this particular example, we change the pattern in a way that we have a different number of bank conflicts in every access. Not in every access, but we repeat again and again up to 256 times, as you have seen, using the same number of colliding threads. But in this case, they are colliding on the same bank. The conflict is in the bank. And this is why the bank conflict doesn't cause so much increase of the latency. And between each of these 2 dots, what we have is a shorter latency, in this case 32 cycles, because we have a bank conflicts, but there is no lock or position conflict. So for example, we may have one thread updating element 0, another thread updating element 32, the next one updating element 64, and so on. There is no position conflict, there is no lock conflict, because they are using completely different locks, but they are in the same bank. And this is why we see that this increases. The total latency increases as we increase the number of conflicting threads. And we can also try different strides as well. Instead of updating, instead of provoking the bank conflict by updating element 0, 32, 64, and so on, we can use a different stride. For example, 256. If we use a stride of 256, we have one thread, and let's say our bank conflict degree M is equal to, we are going to have one thread accessing element 0, another thread accessing updating element 256, and the rest of threads accessing different banks, so they don't cause the bank conflict, right? But we keep increasing the number of threads, right? And at some point, notice that we have one thread updating address 0, the next one address 256, the next one address 512, the next one address 786, and the next one address 1024. So when we increase the stride to 256, every time that we increase the number of conflicting threads by 4, we are incurring an extra latency. That's why the shape of this line here is kind of a curve, and this happens because from time to time we have a lock conflict, or we have lock contention, and these small gaps here that are indicated by the arrows are larger than the gaps that are between these previous dots, and that reflects that there is a lock conflict, because we have threads updating different memory locations that share the same lock bit, as we will explain before. And one of the ideas that we had here was, instead of using a linear hash function as the one that you can see on the slide, we could try to use configurable hash functions. We could change the hardware in a way that we tailor this hash function for the specific problem that we are trying to solve. And by using that, well, the first thing that we tried actually was something as simple as a hash function based on XOR operations. So instead of reading directly the log, the specific log from here and the specific bank from here, what we can do is accessing the bank or the log after XORing some of these bits with some of these bits here, or some of these bits with some of these bits here. So this gives us some hash values and generated by this hash function. And instead of, for example, for this address 32 to correspond this log address, it's probably going to correspond a different one. And what this means is that when we start increasing the stride, and as we did in our previous experiments, remember stride 32 and stride 256, instead of observing how the total latency increases when we increase the conflict degree here or here, you can clearly observe that by using the XOR-based hash, the latency remains much more flat, because we are reducing a lot the number of bank conflicts and the number of logs of log conflicts. If you are interested in these kind of techniques, by the way, I already mentioned these kind of techniques when we talk about the bank conflicts in shared memory in the performance considerations lecture. But if you want to learn more about these techniques, you can check these two papers that are here at the bottom. But before proposing that change, or before any other architectural improvement, we were also thinking about how we could optimize the histogram computation even more. And instead of using a single subhistogram per block, what we can do is using more subhistograms per block, right? That could be one way of approaching the problem. Instead of using a single subhistogram in the shared memory, if you have more space in shared memory, why not placing even more subhistograms, because this way we are going to reduce the amount of contention on the single subhistogram in shared memory. And here you can see one example where instead of using one subhistogram per block, we will be using 4 subhistograms per block. In this case, subhistogram 0, 1, 2, 3, 4, and these threads 0, 1, 2, 3, 4 are going to update different subhistograms. For example, we can tell this thread 0, you always update subhistogram 0. This thread 1, you always update subhistogram 1, and so on. And this way, we are also reducing the contention of the atomic operations in shared memory. But remember, depending on what's the size of the subhistogram, we may end up having band conflicts, right? Actually, in this particular picture, this particular configuration here, if these 4 threads here have to update all of them the same being one in the corresponding subhistogram, they would also be accessing beans that are stored in the same bank. So we have bank conflicts here, and we may also have log conflicts as well. So one idea we had was using simple padding after each of the subhistogram. We just leave one empty memory address in order to shift the subhistogram a little bit. And in case that these 4 consecutive threads have to all of them update the same bean in different histograms, they would be updating these beans in different banks and also in different logs as well. And this way reducing a lot the contention due to bank conflicts or log conflicts, as you can see. And this is something that happens very frequently, because remember, in natural images, in real images, it's very common that consecutive pixels or near-boring pixels have the same values. And in those cases, we would incur these conflicts. And you can even see what was the effect of this software optimization in Fermi and Kepler architectures. These are results for 100 natural images. And here on the y-axis, you see execution time of this histogram kernel. And here we have the 2 sizes of histogram, a histogram with 64 beans and another histogram with 256 beans. And this replication factor is essentially the number of copies of the subhistogram, of the number of replicated subhistogram per each individual thread block, right? And this is why, because we are using replication or these multiple subhistogram, and we are also using padding, that we can reduce a lot the number of position conflicts, the number of bank conflicts, and the number of log conflicts as well. And we see how the performance improves as we increase the replication factor in both cases. Obviously, the maximum replication factor that we can have, because the size of the shared memory is fixed, depends on the histogram size. That's why we can use many more copies of the subhistogram for 64 beans than for 256 beans. But at some point, the hardware improved, the architecture improved, and we started to have native atomic operations in the Maxwell architecture. And this is the result of using this replication technique, these multiple subhistograms per thread block when running these programs on the Maxwell architecture. As you can see, the final performance is completely flat. This is really interesting. We don't need to replicate the subhistograms. We don't need to use more than one subhistogram per thread block, because as you see, the performance remains completely flat. And this is because the atomic operations in Maxwell are so much optimized, the hardware is so much optimized, that these optimization techniques, these software optimization techniques, don't make sense anymore. And I can even show you another example I mentioned in the beginning of the lecture is string compaction. But in this case, string compaction is done. There are very fancy ways of doing string compaction, and we will probably talk about them in a later lecture. But the most naive or straightforward way of implementing a string compaction is by using a counter. You can have this counter in global memory, or you may have multiple counters in shared memory. Every time that we need to compact one value, the particular thread reads one value, checks if the value needs to be written into the output. And if that's the case, it goes to the counter, updates the counter gets one index, and this is the place where it's going to write in the output array. And here you can see the fraction of filter or compacted elements as this fraction of compacted elements increases, this means that we have to update the counter more frequently, so there are more conflicts. And if that's the case in Kepler, you can see how the execution time increases essentially by 1 order of magnitude, or almost 1 order of magnitude. However, the increase when updating a single counter by all threads being involved in the computation increases only like 2 times, or a little bit more than 2 times. But as you can see, it's much more flat, this curve, than this other curve for the older Kepler architecture. If you want to learn more about this type of string compaction, I would also recommend you this interesting post in one of CUDA blogs. And by the way, you might be asking yourself, oh, what does Maxwell have in the shared memory to be so fast when executing atomic operations in shared memory? Well, I don't really have any details about how the hardware is built, but I can show you, for example, this picture that comes from one white paper from AMD, where they also describe their shared memory. In this case, it's not called shared memory. In AMD is called local data share, as you can see on the screen, or LDS. But this shared memory, or this LDS, is also composed by multiple memory banks, as you can see on the screen. And near these memory banks, there are some integer atomic units that have direct access to the memory banks, and this way can execute atomic operations much faster. And not only that, also these LDS include some conflict detection and scheduling logic here to detect the potential conflicts in the execution of atomic operations, and based on that, schedule the threads on these integral atomic units in a way that the number of conflicts get reduced, and the performance of the atomic operations in the LDS, or the shared memory in AMD architectures, is greatly improved. Okay, if you guys don't have any questions, then I'm going to explain what has been the evolution in for the atomic operations on global memory, and after that we will be done. In the global memory, of course, there have also been a lot of improvements over time. In the very first generation, atomic operations were executed in DRAM. That's why, remember that I explained before, this long latency of going through DRAM, bringing some data, updating it, and then writing it back to DRAM. This was very costly in terms of cycles, so that's why the Fermi architecture already, by incorporating the L2, was able to accelerate the atomic operations a lot, these atomic operations in global memory, also because of the fact that it incorporates some atomic units near L2 in a similar way as what we have just seen for the LDS memory in AMD architectures. You can place some small atomic units near the L2 to perform the atomic operations faster. But still, the performance wasn't amazing for the global memory atomic operations in Fermi near the L2. So these atomic units were improved by incorporating some local cache or local buffer to store partial results and accumulate faster when executing the atomic operations. And we are going to we are going to see a comparison of the execution of atomic operations on global memory for these different architectures. The latest update I'm aware of in the architectures is that Pascal supports 64-bit floating point atomic adds on global memory. And here you can identify in this picture that we have a GPU, and the GPU is composed by these processing cluster array, which are essentially the GPU cores. There is a crossbar unit to access these partition units, and from them we can go to the DRAM. Each of these partition units in reality is part of the L2 cache. As you can see on the screen, here we have the L2 cache, and here we have something called ROP. This ROP is in reality one of these atomic units near the L2, but we can even look closer into the implementation of this partition unit, and here we can identify this part here, which is the L2 cache. You can see that there are several slices of L2 cache, but in reality, this is all like a large memory array where we can store the data, the cache lines that we bring from DRAM. And here in the upper part, you can identify the ROP, which is the atomic unit with its own ALU, and also this space here is the local buffer. All these pictures are coming from this patent that you can see here at the bottom. I have no certainty of whether the actual implementation and the real GPUs is like that. No idea about that, but based on the fact that we know from some documents and papers from others that there is the atomic units near L2 were extended with some local buffer in the Kepler architecture, it's likely that something similar to this is implemented in the real architectures. And now we are going to compare the performance of the atomic operations for these different generations over time, from the older Tesla architecture to the newer Maxwell architecture. And we do it by using two simple kernels that represent one of the most important say workload transformations that we can use in our programs. It's what we call the scatter versus gather parallelization approach. In the scatter approach, what we do is assigning input elements to the threads, right? So we are going to have one thread reading this input element, this thread 0, thread 1, and so on, and then all of them updating the output wherever they have to go. Notice that this is the approach that we have followed in the histogram calculation. And the other possibility is a gather parallelization, where we have the multiple threads being assigned one element of the output. For example, this element 0 of the output is assigned to thread 0, and then each thread has to go through the whole input to see if the value is worth updating the output value, right? So there are different ways of doing both things. Maybe some of you might be asking, oh, why don't you use a gather parallelization for the histogram calculation? Yeah, that could be a possibility, but we don't expect it to be very efficient. And why is that? Because the output is a histogram, right? And this element here is going to be the bin 0. So bin 0 is only going to be updated if the corresponding image pixel has the value 0, right? And now with this approach, we need thread 0 reading the whole array, looking for pixels of value 0 to update the corresponding bin. And as you can imagine, this is pretty costly because all threads need to read the whole image. And the output is probably pretty small, maybe a 256 bin histogram, but the input is pretty large, right? This may have hundreds, thousands, or millions of elements. So trying that or pretending that each of the threads reads the whole image is going to be super costly, and that's why gather parallelization is not a good approach for histogram, and this is why we use this gather parallelization in histogram computation. But you can find many good examples that use gather parallelization, and they are pretty successful. Matrix multiplication, for example, is an example of gather parallelization that we have explained in the past, where each of the elements of the output matrix is assigned to a different thread. And these are the two simple codes. I'm going to leave them here for you to check more in detail, but you can already see that in the scatter kernel, we are using atomic operations. We need to use them. The reason is that we may have multiple threads updating the same element of the output. And then we have the gather parallelization, where we assign the output elements to the individual threads. And as you can see, there are no atomic operations at all. The goal of these experiments is just to see how the atomic operations have evolved over time. The performance of these atomic operations on global memory has evolved over time, and also compare their performance to the gather implementation, which in principle is going to be more efficient because there is no serialization due to the atomic contention. But one interesting thing that you're going to observe is that the advantage of the gather parallelization is also getting reduced over time as the implementation of the atomic operations improves. And here you can see some results here for the gather approach. And these are results for the scatter approach with two different input data sets. One of them doesn't cause any conflict, any atomic conflict. The other one causes a lot of atomic conflicts, as you can see. And these are execution time results in Tesla, Fermi, Kepler, and Maxwell architectures. So in the case that we have conflicts, we see how in Tesla, which needs to go to DRAM to fetch the data and modify it and then write it back, you see that whenever you have conflicts, and these numbers here determine the size of the arrays that we have used in the experiment. So the larger the array, the more conflicts there are. So you can see that there might be more conflicts, and also the execution time increases as well because the array is longer, obviously. But you can see how this execution time for Tesla ramps up when we have conflicts. Then that's why that's because Tesla executes the atomic operations in the global memory, and there's no L2 cache. But we can zoom in and check this part of the plot here, and we see that even though Fermi has atomic units in L2 cache, still we see that its performance goes super bad and increases a lot. We have managed to reduce the total execution time by an order of magnitude compared to the execution on Tesla, which is the blue line here, but it still is much more costly than using the gather approach. And then we can go even closer and compare how the local buffers in Kepler architecture have improved the performance of the atomic operations even more. So we get another 10x speed up thanks to the local buffers. And then we have Maxwell, which is slightly better because it's a newer generation, at least in this particular experiment, is slightly faster, as you can see. And one interesting observation is that, as I said before, also the gap between the gather approach, which is way more efficient here than the scattered approach, is also getting reduced as we increase, as we improve the hardware over time. And this, just to finalize some final results, execution time results, this is 256 being 256 being histogram computation for 100 natural images. In this case, we are not using any fancy optimization. We are only using one private histogram, one private subhistogram per block in the shared memory implementation. And we compare here for Fermi, Kepler, and Maxwell architectures, the execution of the histogram computation in the when using privatization in shared memory, or simply using a single histogram in global memory. And you can notice how interestingly the execution time from Fermi to Kepler goes down very, very quickly. And actually, if in Kepler you don't use replication, you just use a single private histogram or subhistogram per block, the execution time is essentially the same, because atomic operations in shared memory didn't improve in this architecture, but atomic operations in global memory improved a lot, as you can see. And only in Maxwell architecture, we also see that the execution time when using privatization in shared memory also gets reduced a lot, and somehow it again rebalances the differences between shared memory, which is supposed to be much faster, or is much faster than the global memory. So this is more or less the evolution of the atomic operations, but the most important thing today is that you are already familiar to how parallel histograms, histogram computation is performed. You have also been introduced to atomic operations and an important technique that is privatization, and we will likely talk about privatization in a later lecture as well. If you want to read more about this, histogram computation, atomic operations, and privatization, I can recommend you this chapter 9 in the Programming Massively Parallel Processors book. And this is all for today, from my side at least. I don't know, guys, if you have any questions. I don't see any questions in YouTube. I hope that everything is very clear. As I said, most important thing is to focus on how the histogram is built. The other part is completely optional. I just wanted to explain you how the atomic operations evolve, because it's something that I did all these analysis that I showed. Something I did in the past during my PhD thesis, and it's I still have I'm still very interested on the execution of atomic operations, not only on NVIDIA architectures, but also other parallel architectures as well. Okay, no questions? Okay, no problem. Thank you very much, everyone, for your attention. Hopefully everything was clear. Don't hesitate to contact me later if there is something that you want to ask or you need to clarify.